In this paper, we introduce a new method for load-responsive, inhomogeneous, and anisotropic lattice generation based on ellipsoid packing. With increasing ease of fabrication through additive manufacturing technologies, 3D lattice structures are widely used in architectural and design fields, as well as in biomedical and aerospace engineering. They have the ability to achieve high mechanical performance while maintaining a light weight. This example shows the hip implant design, which causes less stress shielding and meets mechanical requirements. Although it's easier to fabricate lattice structures, there's limited information available in the literature about designing them in large scale. This gap is especially apparent when it comes to random inhomogeneous lattice structures and the related generation and evaluation strategies. This paper aims to address this gap by exploring the advantages of inhomogeneity and anisotropy in 3D lattice structures within architectural load-bearing applications. Inhomogeneity and anisotropy are favored in natural load-bearing structures, such as a bone's trabecular lattice, and serve to achieve lightweight and high mechanical performance. Within the context of bone's trabecular lattice, responsive inhomogeneity occurs as a result of thickening and thinning of trabecular struts in relation to high and low stress stimuli. Anisotropy occurs through the trabecular orientations being parallel to the direction of pertinent compressive forces. Establishing the trabecular bone as a natural precedent, this paper introduces a novel computational method for controlled load-responsive inhomogeneity and anisotropy in 3D lattice generation. The primary focus is presenting streamlined algorithmic processes of informed and responsive lattice generation. This workflow expands upon our previous work, Polybrick 2.0. The methodology of this paper contains two parts. The first part is the generation workflow. The second part is comparative studies, which evaluates the effectiveness of the generated lattices. For the generation workflow, we first look into the morphological quantifiers of trabecular bone. The trabecular bone lattice is quantified by the parameters of trabecular number, separation, length, and orientation. In our workflow, these quantifiers are interpreted as controllable load-responsive parameters. For this interpretation, ellipsoids are introduced as media. This animation shows the overall process of lattice generation. A number of ellipsoids are densely packed in the design geometry. Through a secondary procedure, kissing ellipsoids, the centroids of the touching ellipsoids are connected with a line segment. The morphologic parameters of trabecular number, separation, and orientation are thus controlled by the ellipsoid size, distribution, and orientation. Then, we introduce tensor field as a key input that establishes load-responsive inhomogeneity and anisotropy in the process of lattice generation. The tensor field is defined by a field of 3 orthogonal tensors at each point within the design geometry. For each ellipsoid, the 3 tensors interpolated at the centroid serve as a response condition in determining the length and orientation of the axis. The tensor field input can be generated in multiple ways. In this paper, ANSYS is used to apply finite element analysis to the design geometry under a set loading condition. For each node in the finite element model, maximum, median, and minimum principal stresses are calculated as the 3 orthogonal tensors in the tensor field. The generation workflow is implemented using C#. It provides multiple inputs that serve as response factors in determining the lattice geometry. These inputs include boundary geometry, tensor field, maximum ellipsoid size, minimum ellipsoid size, and pre-existing ellipsoids. The lattice generation workflow starts with producing a tensor field for the boundary geometry with the help of ANSYS. The boundary geometry is first analyzed as a solid in ANSYS using a user-defined loading condition. Then, a CSV file containing the key parameters can be exported and translated into a tensor field. The dense packing is realized by iteratively adding the new ellipsoids and relaxing the existing ellipsoids. In each iteration, collisions are checked between pairs of ellipsoids. This process is very complex and computationally expensive for ellipsoids because the ellipsoid collision point doesn't necessarily sit on the line that connects the centroid as it does in spherical colliding. To simplify this process, the orientation difference of the two colliding ellipsoids is assumed to be small. Hence, the collision point is still assumed to be in close proximity to the connection line. For each pair of ellipsoids, the sum of the two rim distances along the center connection line is calculated and then compared to the centroid distance. If the sum is greater than the centroid distance, they're determined to be colliding, otherwise not. If no collision is detected, indicating all the ellipsoids are fully relaxed, then one more ellipsoid will be added into the boundary geometry. If collisions are detected, a relaxation process will happen, and the colliding ellipsoids will be moved away from each other by half of the overlapping distance. After the collision detection process is completed, the ellipsoid sizes and orientations are updated according to the tensors interpolated at the new centroid locations as a response to the tensor field. And semi-axis lengths are determined by both the tensor magnitudes and the user-decided maximum and minimum ellipsoid size. Generally, an ellipsoid is expected to be smaller when the tensor magnitudes are higher, and is to be oriented towards the largest of the three tensors. Those are slices taken from a packing process at different iterations. When no more ellipsoid can be added to the design geometry, the packing process will terminate. The 3D lattice is then generated by connecting the centroids of the casing ellipsoids. This procedure allows for the adjustment of the number of struts by changing the casing tolerance. Here shows the original tensor field and the generated lattice. In order to evaluate the effectiveness of the workflow, several lattices are generated and tested using ANSYS. Control lattices for comparison include both cellular periodic lattices and other inhomogeneous anisotropic lattice precedents, such as sphere packing followed by 3D Voronoi, ellipsoid packing followed by 3D Delaunay. To begin the quantitative comparison, lattices are generated with identical boundary sizes. When the line bodies are moved to ANSYS, they are all piped by 2 mm. The total amount of force applied to each lattice is kept the same by dividing a load of 1000 Newton across the top face vertices of each lattice. Controlling these parameters simplifies the post-processing of the axial force and directional displacement data because only lattice length is uncorrected for. Some lattices have a longer total strut length, meaning there's more material contained in the bounding box. They inherently perform better. To adjust for this, stiffness per volume is calculated. The maximum axial force and directional displacement data without this length correction are also reviewed to get a general sense of the performance of the lattice. As the interest group, 2 ellipsoid packing lattices are tested, one generated with a uniform loading condition input and the other with a point loading input. The result illustrates how our lattices perform in stress, deformation, and stiffness against the control lattices generated with other algorithms. An optimal lattice for load-bearing applications would minimize the highest stress found in the strut elements, minimize the maximum deformation of the lattice, and maximize the stiffness because the force would be most evenly distributed and protect the lattice from breakage. The ellipsoid packing lattices formed with uniform loading and point loading both show higher stiffness per volume than a majority of the other lattices. However, there are limitations for this result. We chose the piping radius of 2 mm based on the expected dimensions of our physical prototypes. But each individual lattice does have an optimal piping diameter to maximize the performance. Hence, We may not have chosen the ideal radius for the ellipsoid packing algorithm to demonstrate its full potential, or we may have chosen a radius that causes other lattices to perform poorly. So the current results should only be considered on the scale of those prototypes. If we want to change the scale or extrapolate the results, more testing would be needed to explore the dependence between the performance and piping radius. As a conclusion of this paper, a new computational method based on ellipsoid packing is proposed and evaluated for the generation of anisotropic and inhomogeneous lattice structures. A Grasshopper plugin is also formalized and will be available soon for designers to use. For the next phase, additional researches of material and fabrication will be performed to leverage this method in architectural projects. Thank you for watching.